Good afternoon, my fabulous chemistry students. Video number 10, Unit 1, Significant Figures. We will be able to, when we are done, determine which figures have meaning in measured numbers, and we will be able to then use our rules to support and report out those numbers that have sig figs after we've done calculations. So what is a significant figure? Well, we're going to do many calculations and measurements. Basically, they are the real numbers, okay? So I want to eliminate this, what we call calculator barf, numbers that are just there, that don't have any meaning to me. And it's going to come into play because here's some big numbers we use. There's the speed of light. That number is enormous. Well, if I take a smaller number and I multiply it by it, you're going to see that the smaller number is going to end up limiting what numbers I can actually report, which is nice. I don't answer with the big ones. So on to the notes. Sig figs is short for significant figures. You're going to hear me say that a lot. It's a method for handling our uncertainty or our error in our measurements that we're learning about. This arises due to the fact that equipment has different forms of accuracy. Not everything is as accurate as we would like it to be. And significant figures are the measured value to the measurement. Okay, so we're going to just take a real quick check at estimating and measuring. Ready? We know for sure that on this ruler, that arrow is definitely more than 2, right? And it's definitely below 3. We're all good there. Then if I keep going, so this is 2.5, 6, 7, 8. It's actually more than 2.8, isn't it? But it's less than 2.9. We're honing in on this now. The ruler allows us to estimate the length 2. Well, if I go about halfway in between these two pieces, this would be 8.5 here, and this is to the left of it a little bit. I'm going to say 283. Okay? The estimated value is allowed. Last, we're going to read from the bottom of the meniscus. You guys heard this before from Living Environment? Meniscus is this thing here. That shape, we'll understand why that shape comes at a later date, but for right now you need to know we take that bottom measurement. So it's definitely above 25, 26, 27, but not to 28. It's approximately 27.5. That 0.5 is key. We need to be able to estimate those numbers. This is the Atlantic Pacific method. I want you to take a minute and read this, and I'm going to try and keep the video short. I'm just going to apply it to the practice, okay? You read it, you pause it, you read it, and then here I'm going to go on now, here unpause. Now let's practice. Ready? Determine the number of significant figures below. Okay, number 1, no decimal present. So that's Atlantic. It's absent. So I'm going to go from the right to the left. It says start at the first non-zero and count. That's 3. Number 2, decimal point is not present. It is absent. So I'm going to start on the Atlantic side and go to the Pacific side. 1, 2, 3, 4. Nope, that was a mistake, Mr. Milks. Mr. Milks. So let's start at the first non-zero, Mr. Milks. Please don't make mistakes in your notes, Mr. Milks. Students don't like that. Thank you. Number 3, present. So I'm going to start at the Pacific coast. Go right. Start at the first non-zero number. Count all numbers. 4. Here is a very good example of why significant figures are important and why they are a little tricky. Looks to me like the same number. The only thing that's different, of course, is the decimal point. That decimal point makes this 0 a much more real number than this 0. And that's what the rules state. So that's how we're doing it. Number 4, decimal point present. Start at the left, go right. Start at the first whole number. 1, 2, 3. 3 sig figs. 0, 3, 5, 7. Decimal point is present. Start at the first whole number, and it goes to 3. Number 6, decimal point is present. Start at the left. 1, 2, 3, 4. Significant figures. Again, number 7, decimal point is present, so we'll start at the Pacific and work our way to the Atlantic. Start at the first non-zero. 1, 2, 3, 4 significant figures. So there is a walkthrough for practice. Let's talk real quick about significant figures. All non-zeros are always significant. These numbers are important, okay? Number 2, zeros located between non-zeros are significant. We call these sandwiched zeros. Okay? Sandwich zeros are important. That's this one here and this one here. Those are considered measured because we actually measured these last numbers. Okay, so measured numbers is what we're looking for. For numbers less than 1, all zeros to the left of the first non-zeros are non-significant. So that's these guys here and these guys here. And that fits into our Pacific rule because we would start on the left and go to the right, starting at the first non-zero number, according to Atlantic Pacific. Okay? Zeros at the end of a number and to the right of a decimal point are significant. So again, this falls into our Pacific. I have a present. I'm going to go left, start at the first non-zero, and count every number. That is consistent with our Pacific method. They are also considered measured because this number, because of the decimal place, these zeros, because they're there, are all very, very significant. Okay? It's even more zero than not. Oh, excuse me. Sorry about that. Zeros at the end of a whole number may be or may not be, depending on whether or not there is a decimal. Again, Pacific, Atlantic. This one's Atlantic. I'm going to read this way. This one's Pacific. I'm going to read this way. This one starts there. I have one significant figure. This one starts 1, 2, 3, 4. 4 significant figures. Same number, different amount of significant figures because of that pesky decimal. Number 6, exact numbers, infinite. Practice for you. You guys do the practice. We will talk about it in class and check your work. Now, when I do calculations, let's get right into it. Multiplication, I'm going to perform my operation as normal. I'm going to express my answer in the least sig figs. So if you see the 12, 5, 7, 5 sig figs, start at the left, count to the right, 5. This 1.162 has 4. My answer then, when I plug it into the calculator, is this. I have to stop at the 4 sig figs, to give me an answer of 14.24. These numbers, even though my calculator barfs them out, are not measured. Because this one stops at 4, I can only use 4 answers. We call those like the real numbers. They are the measured numbers. The other numbers aren't. So it kind of fakes it that they're there, and we don't really know they're there because we didn't measure them. Addition and subtraction. Line up the decimal points. Use the one with the least amount of decimal points as where we stop. So if I add these guys together, without the pen in my hand, I will get 220.429. But this 6 here is the one that's going to limit it. It's the least number of sig figs. So my answer will be 220.4. See, the 2 and the 9 will fall off. They are not measured anymore. You have examples now. You're going to subtract the first one. This is divide on the second one. And you're going to use the rules that we just learned. More practice for you to check in class. Ready? Go. And I continue. Scientific notation. Oh, Mr. Milks, you're killing me. You got more numbers, Mr. Milks? What's all these numbers? Well, I think we're getting about to the end. So, addition and subtraction. I must have the exponents the same. Then I add or subtract the mantisses, or those numbers in front. So let's do this real quick. Are the 6 and the 5 the same? No. So I can make the 6 5 or the 5 6. I prefer to make the 5 6, which is going to make 0.23 times 10 to the 6. 4.5 times 10 to the 6. Now it's 2.5 minus 2.3. Handy dandy calculator. Minus 0.23 equals 4.27 times 10 to the 6. Just bring this right along with us. That's why we switched it at the beginning, okay? Now for multiplication, we're going to multiply the mantisses, and then we're going to add the exponents. So let's do that real quick. 3.1 times 5.01 equals 15.531 times 10 to the, it says, and then the exponents are added. So 3 plus 4 is 7. Bam. Division. And mantessas are divided, and then we subtract the exponents. So this is 7.63 divided by 8.6203. 7.63 divided by 8.6203 equals 0.88512 times 10. I have 3 minus 4 to the minus 1. I'm going to scooch this guy up, make him 8.8. But how many numbers do I go, Mr. Milks? 1, 2, 3. 1, 2, 3, 4, 5. 3 is my limiting factor, so I'm going to do 3 numbers times 10 to the minus 2. Now, if you give me this, this wouldn't be wrong, but when we studied scientific notation in the past, we said that the mantessa needs to be between 1 and 9. So this, it's technically not right, but either these numbers are actually equivalent, okay, in your calculator. So now you should be able to estimate the last digit when we do length and measurement, be it with a ruler or a graduated cylinder. We can apply significant rules to determine which numbers are real and which ones aren't. As far as how many of them are significant and aren't in a number, then we can go ahead and apply that to our calculations, and we are done with Sig Figs, Mr. Milks. Good job, everybody. I'll see you tomorrow in class.